So what's the problem here? Well, remote-controlled quadcopters are currently one of the quickest growing tech fields, and it's easy to see why. They can capture incredible aerial footage that can be used for all kinds of reasons. Due to increased popularity, we must continue to innovate new flight control systems to improve the user's flight experience and overall safety. As the FAA continues to further limit the use of quadcopters due to privacy and safety, especially in public or crowded areas, it is becoming increasingly important that we can ensure a safe and predictable flight 100% of the time. By using a feedback-based control system and user inputs, we can create a system that is more predictable and more consistent than ever before. So, what exactly are we trying to accomplish? Well, through our control system, we intend on providing the quadcopter an increased level of autonomy. Our goal is to improve the quad's transient response and minimize steady-state error in the system by using a control system that compares current altitude with desired altitude and makes adjustments accordingly. Designing our model. So, how do you even start to design a model for a system like this? Well, we began by drawing an FBD, or a free body diagram of our system. As you can see, the purple rectangle labeled M, that represents the mass of our system, or the mass of the quad itself. Pulling straight up from that is our FR, or the force that the rotors are generating. Underneath the purple rectangle, you can see our B value. This represents the dampening the quad experiences as it moves through the air. And finally, pulling straight down on our system is FG, or the force of gravity. As you can see, MH double dot plus BH single dot equals F net, or the net force on the system. Alright, here you can see I drew a simple block diagram of our open loop system. A block diagram correlates our outputs to our inputs and what goes in between. But what is G of S? Well, G of S is an equation that will correlate our outputs and our inputs. But how do we find that? Well, first we used the mechanical drawing from the previous page and turned it into an impedance network. Here, you can see we have our FR, or force from the rotors, representing a current input. We also have two impedance devices, one for the mass of the system and one for the dampening value. Now, to find how our outputs correlate to our inputs, we have to find the equivalent impedance of our system. And to do this, we just use the parallel combination equation we learned in circuits. And our Z equivalent is our G of S, 1 over ms squared plus bs. So now you might be asking yourself, what numbers do we put in for the variables m and b? Well, in this case, m is equal to the mass of the quadcopter. After researching a few brands of quadcopters, we thought that 1 kilogram was a nice, round, reasonable weight for our quad. And now the variable b, it's equal to our dampening value, the dampening of the blades moving through the air. After extensive research, we had difficulty finding exactly what this value should be, but 0.7 seemed to be a reasonable number based on the information that we did find.
Now it's time to analyze our system. The diagram shown is the Simulink model of our open loop system. This model takes into account disturbances such as wind, frame flex, turbulent airflow, or rapid temperature changes. The G of S function we generated previously turned out to not be bibostable. This is shown by the step response of our system, which, as you can see, goes to infinity. This will be remedied in the design section of this video. For this application, we decided that a PD controller was the only type of controller that would meet our design goals. Because our system is a Type 1 system, a PD controller results in zero steady-state error. Shown is the open-loop root locus of our system. Our open-loop transfer function has no zeros, but has poles at 0 and negative 0.7.
How the system was designed. In order to create a stable signal, we decided to implement a PD controller, as this will give us the zero necessary to make our system stable. We determined that a settling time of 10 seconds or less, a percent overshoot of 10% or less, and a steady state error of less than 0.1 were both feasible and reasonable. As we have a step input, with a Type 1 system, the steady state error will always be 0. Using MATLAB's CISO tool, the PD controller was implemented and the requirements were set. Through use of the PID tuner, a KP of 2.019 and a KD of 0.03344 provided a stable system that met the design specifications. By implementing a PD controller, we now have safe control over the quadcopter's height. How the results were verified. In Simulink, a PD controller block was added and the KP and KD values previously mentioned were initialized. This data was used to test the system step response of the closed loop system and to ensure the design specifications were met. With this PD controller in place, we were able to achieve a settling time of 3.48 seconds, about 1/3 of what was specified, and a percent overshoot of 6.32%.
But is our design robust? Let's explore. To calculate gain and phase margins by hand is simple. For gain margin, start at the frequency where the phase Bode plot meets 180 degrees. Follow this frequency up to the magnitude Bode plot and measure the distance to 0 dB magnitude. This is the gain margin. For our application, gain margin was infinity. Calculating phase margin is just the opposite. Start at the frequency where the magnitude Bode plot meets 0 dB and move down to the phase plot. Measure the distance to 180 degrees and this is the phase margin. For our application, phase margin was 76.4 degrees. The crossover frequency can be obtained from the magnitude Bode plot as well, corresponding to the frequency where the plot meets 0 dB. For our application, this was 1.82 radians per second. To calculate the time delay, convert the phase margin to radians by multiplying by pi and dividing by 180 degrees. Then divide this number by the crossover frequency to attain the time delay. For our application, this was 0.73 seconds. These values were verified by our CISO tool model, and the time domain analysis was further verification for these results.
In conclusion, we were successfully able to design a feedback-based control system to take control of our unbound plan function. We were able to meet and exceed all of the design goals that we had set forth. Thanks for watching.